Hey there. How was your day? Wherever you are in the world, whatever time it is, I'm so glad you found your way here tonight. We're about to embark on a journey to one of the most mysterious and breathtaking worlds in our solar system. A world that has captivated humanity for thousands of years, yet holds secrets so profound that even our most advanced spacecraft continue to uncover new mysteries with each passing orbit. Tonight, we're traveling to Saturn. But this isn't the Saturn you learned about in your textbook. This isn't the simple gas giant with pretty rings that your teacher showed you in that grainy photograph. What we're about to explore together is a world so strange, so magnificent, and so utterly alien that it challenges everything we thought we knew about planetary science. If you find comfort in these gentle explorations of the cosmos, I'd be grateful if you'd consider subscribing and liking this video. It helps more curious souls like us discover these cosmic mysteries together. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the rings of Saturn alongside me. I'd love to know where you're watching from tonight. Feel free to comment your time and location below. Are you gazing up at the stars from your window right now? Perhaps Saturn itself is visible in your night sky, that steady golden point of light that has watched over Earth for billions of years. There's something beautifully humbling about discussing this distant world while we're all scattered across our small planet, each of us under the same cosmic dome. Let's start. What your teachers never told you about Saturn could fill libraries. They never mentioned that Saturn's rings sing. They never explained that this planet has moons where it might actually rain methane from hydrocarbon clouds. They certainly never described how Saturn's magnetic field creates auroras so powerful they could engulf our entire Earth. And they probably never shared the mind-bending fact that Saturn is less dense than water, meaning this colossal world would actually float if you could find an ocean large enough to contain it. Welcome to the Saturn they didn't want you to know about, the Saturn that defies physics as we understand it, the Saturn that holds keys to understanding not just our solar system, but the very nature of planetary formation throughout the universe. This is a world where diamonds might rain from the sky, where moons harbor hidden oceans that could support life, and where the fundamental laws of physics play out in ways that still leave our greatest scientists speechless. Let's begin this gentle descent into one of the most extraordinary stories our solar system has to tell. Of story beauty, mystery, and cosmic forces so powerful they reshape our understanding of what's possible in the vast theatre of space. You probably remember Saturn from school as the planet with rings. Simple enough. But what they never told you is that Saturn's relationship with its rings is one of the most dynamic and violent processes in our solar system. These aren't static, peaceful circles of ice and rock gently orbiting a distant world. These rings are alive with motion, constantly being destroyed and reformed in a cosmic dance that has been playing out for millions of years. The rings of Saturn extend outward for hundreds of thousands of kilometers, yet they're remarkably thin. If you could shrink Saturn's rings down to the size of a football field, they would be thinner than a piece of paper. This creates an optical illusion that has fooled astronomers for centuries. From certain angles, the rings completely disappear, making Saturn appear as just another ordinary planet. But when viewed edge-on, these impossibly thin structures reveal themselves to be among the most complex and beautiful formations in our solar system. What's truly extraordinary is that these rings are not solid. They're composed of billions upon billions of individual particles, each one orbiting Saturn at its own speed, according to the precise mathematics of orbital mechanics. The inner particles race around Saturn faster than the outer ones, creating waves and patterns that ripple through the rings like cosmic tsunamis. Some of these waves tower hundreds of kilometers high, casting shadows that stretch across the ring plane like mountain ranges made of ice and stone. But here's where the story becomes even more fascinating. Saturn's rings are not permanent fixtures. They're constantly being fed new material from Saturn's moons, while simultaneously losing particles that either fall into Saturn's atmosphere or escape into space. This means the rings we see today are not the same rings that existed when dinosaurs walked the Earth. The rings of Saturn are constantly renewing themselves, a cosmic recycling system that has been operating for eons. The most remarkable discovery came when scientists realized that Saturn's rings actually create music. As charged particles from Saturn's magnetosphere interact with the ring material, they generate radio waves that can be converted into sound. When Cassini's spacecraft recorded these signals and played them back as audio, scientists heard something that sounded eerily like a cosmic symphony. The rings of Saturn literally sing as they orbit their parent world, creating melodies that no human ear was ever meant to hear. This musical quality reveals something profound about the electromagnetic environment around Saturn. The planet generates a magnetic field roughly 600 times stronger than Earth's, creating a vast magnetosphere that extends far beyond the rings themselves. This magnetic cocoon traps charged particles from the solar wind, creating radiation belts that would be lethal to any unprotected spacecraft or astronaut. Within this magnetic fortress, Saturn's moons and rings exist in a complex ecosystem of gravitational and electromagnetic forces. The rings themselves are divided into several distinct sections, each with its own characteristics and mysteries. The A ring, B ring, and C ring were the first to be discovered and mapped. But as our instruments became more sophisticated, we found gaps within gaps, rings within rings, and structures so intricate they challenge our understanding of orbital dynamics. Some gaps in the rings are maintained by small moons called shepherd satellites that gravitationally sculpt the ring edges with mathematical precision. Other gaps appear and changes disappear seasonally, responding in Saturn's magnetic field or the gravitational influence of its larger moons. Perhaps the most mysterious feature of Saturn's rings is something called spokes. These are dark, radial features that appear and disappear in the rings like ghostly spokes on a cosmic wheel. For decades, scientists had no explanation for these ephemeral structures. They seem to violate the basic laws of orbital mechanics, appearing to rotate as solid objects, even though the rings are composed of individual particles moving at different speeds. Only recently have we begun to understand that these spokes are created by electromagnetic forces that temporarily lift tiny particles above the ring plane, creating shadows that sweep across the rings like the hands of a celestial clock. The complexity of Saturn's ring system becomes even more apparent when you consider the role of resonances. Just as a singer can shatter a wine glass by hitting the right note, gravitational resonances between Saturn's moons and ring particles can create dramatic structures in the rings. Some resonances clear gaps, while others pile material into narrow, dense ringlets. These gravitational harmonics create patterns that repeat across the ring system, like variations on a cosmic theme. What makes this even more extraordinary is that Saturn's rings are not unique in our solar system, but they are by far the most spectacular. Jupiter, Uranus, and Neptune all have ring systems, but theirs are thin, dark, and composed mainly of dust and small rocky particles. Saturn's rings are bright, massive, and dominated by water ice, making them visible even through small telescopes from Earth. This has led scientists to wonder whether Saturn's rings represent a special moment in planetary evolution, or whether they're a more permanent feature that we're simply fortunate to witness in their full glory. The origin of Saturn's rings remains one of the great unsolved mysteries of planetary science. Some theories suggest they formed from the destruction of a moon that wandered too close to Saturn and was torn apart by tidal forces. Others propose that the rings are the remnants of material left over from Saturn's formation that never coalesced into moons. Recent evidence suggests that the rings might be much younger than previously thought, perhaps only a few 100 million years old, which would make them relatively recent additions to the Saturn system. This youth presents a fascinating puzzle. If the rings are indeed young, what catastrophic event created them? Was it the collision of two moons, the tidal destruction of a comet that strayed too close to Saturn, or perhaps the rings are the remains of a moon that was shattered by impacts from asteroids or comets? Each possibility tells a different story about the violent and dynamic history of our solar system, but Saturn's mysteries extend far beyond its famous rings. The planet itself is a world of contradictions and extremes that challenges our understanding of planetary physics. Saturn is the second largest planet in our solar system, with a diameter nearly 10 times that of Earth, yet it has a density lower than water. This seems impossible until you realize that Saturn is composed almost entirely of hydrogen and helium, the lightest elements in the universe. If you could somehow place Saturn in a cosmic ocean, this giant world would float like a cork. This low density creates unique atmospheric conditions that are unlike anything else in our solar system. Saturn's atmosphere is a churning maelstrom of hydrogen, helium, methane, and ammonia clouds that create weather patterns spanning thousands of kilometers and lasting for decades. The planet's rapid rotation, completing one day in just over 10 hours, stretches these weather systems into bands that circle the globe at incredible speeds. Some of Saturn's winds reach velocities of over 1,800 kilometers per hour, making Earth's most powerful hurricanes seem like gentle breezes by comparison. Deep within Saturn's atmosphere, pressures and temperatures become so extreme that hydrogen begins to behave in ways that seem almost magical. Under these conditions, hydrogen becomes metallic, conducting electricity like copper wire and generating the powerful magnetic field that shapes Saturn's entire electromagnetic environment. This metallic hydrogen ocean might extend halfway to Saturn's core, creating a vast reservoir of exotic matter that exists nowhere else in our solar system, except possibly within Jupiter. At the very center of Saturn lies one of the most mysterious objects in our solar system. Saturn's core is thought to be a mixture of rock, ice, and metallic compounds compressed to densities that dwarf anything found on Earth. This core is likely surrounded by layers of increasingly exotic forms of matter, each layer existing under conditions that we can barely comprehend. The temperatures at Saturn's core may reach 11,700 degrees Celsius, hotter than the surface of the Sun, yet this incredible heat is trapped beneath thousands of kilometers of dense atmosphere and exotic matter. These extreme conditions inside Saturn create phenomena that border on the fantastical. Scientists believe that the intense pressure and heat within Saturn's atmosphere might actually create diamonds. Carbon atoms, compressed under unimaginable forces, could form diamond crystals that rain down toward the planet's core like glittering snow. These diamond raindrops would be unlike anything found on Earth, created in an environment so alien that it challenges our understanding of chemistry and physics. But perhaps the most remarkable aspect of Saturn is how it has shaped the evolution of our entire solar system. Saturn's massive gravitational influence has played a crucial role in determining the orbits of other planets, asteroids, and comets. Some scientists believe that Saturn migrated inward toward the Sun early in our solar system's history before being pulled back out to its current position by Jupiter's gravitational influence. This cosmic dance between the gas giants may have prevented Earth from becoming a barren, lifeless world by ensuring that water-bearing comets and asteroids could reach the inner solar system. The gravitational partnership between Jupiter and Saturn continues to protect Earth today. Together, these giant worlds act as cosmic vacuum cleaners, capturing or deflecting dangerous asteroids and comets that might otherwise threaten life on our planet. Without Saturn's protective influence, Earth might be subjected to catastrophic impacts far more frequently, making the development of complex life much more difficult, if not impossible. As we drift deeper into this exploration of Saturn's hidden nature, we're only beginning to scratch the surface of this world's mysteries. The planet that seemed so simple in your school textbook reveals itself to be a cosmos unto itself, a laboratory for exotic physics, and a key player in the grand story of our solar system's evolution. Saturn's influence extends far beyond its immediate neighborhood, through a collection of moons that reads like a catalogue of alien worlds, each one harboring secrets that could rewrite our understanding of life in the universe. What your teachers never mentioned is that Saturn doesn't just have a few moons like Earth's solitary companion. Saturn commands a retinue of at least 146 confirmed moons, with new discoveries being made regularly as our instruments become more sensitive and our exploration techniques more sophisticated. These aren't just chunks of lifeless rock and ice scattered randomly through space. Saturn's moons form a complex gravitational orchestra, each one influencing the others in ways that create some of the most extraordinary environments in our solar system. Some of these worlds harbour subsurface oceans that may contain more water than all of Earth's seas combined. Others experience seasons that last for decades, with weather patterns that include methane rain, nitrogen snow, and hydrocarbon lakes that dwarf our largest terrestrial bodies of water. The largest of Saturn's moons, Titan, represents perhaps the most Earth-like world we've discovered beyond our own planet, yet it's so alien that walking on its surface would be like stepping into a science fiction novel. Titan is larger than Mercury and possesses a thick atmosphere composed primarily of nitrogen, just like Earth's. But that's where the similarities end and the true wonder begins. Titan's atmosphere is so dense and its gravity so low that a human could potentially fly by strapping wings to their arms and flapping, soaring through skies thick with orange hydrocarbon haze. The surface of Titan is a landscape that defies earthly comparison. Rivers of liquid methane carve channels through hills of water ice as hard as granite. Lakes and seas of liquid ethane and methane dot the polar regions, creating coastlines and archipelagos of hydrocarbon chemistry. The largest of these seas, Kraken Mare, contains more liquid hydrocarbons than all of Earth's known oil and gas reserves combined. Imagine standing on the shore of an alien sea, watching waves of methane lap against beaches of organic compounds, while a pale, distant sun struggles to penetrate the thick atmospheric haze overhead. What makes Titan truly extraordinary is its active geology, driven not by molten rock, but by water ice and organic chemistry. This world experiences a form of volcanism where liquid water and ammonia erupt from underground reservoirs, creating icy flows across the surface. These cryovolcanoes reshape Titan's landscape, just as traditional volcanoes modify Earth's surface, but they operate at temperatures where water behaves like molten lava and organic compounds freeze solid. The weather on Titan follows patterns that span decades rather than days. Massive storm systems migrate across the globe, bringing methane precipitation to different regions in cycles that mirror Earth's seasonal patterns, but operate on completely different timescales. During Titan's long summers, which last about 7 Earth years, lakes in the northern hemisphere gradually evaporate, while the southern regions experience their own unique meteorological phenomena. This creates a global cycle of hydrocarbon precipitation and evaporation that has been operating for billions of years. But Titan harbors an even deeper secret beneath its exotic surface. Scientists of have discovered evident subsurface ocean of liquid water that lies hidden beneath the moon's icy crust. This buried sea may be 10 times deeper than Earth's deepest ocean trenches and could contain the perfect conditions for life as we know it to emerge and flourish. The interaction between Titan's surface chemistry and this hidden ocean creates a complex system where organic molecules could potentially develop into the building blocks of life. Moving inward through Saturn's moon system, we encounter Enceladus, a world that has revolutionized our understanding of where life might exist in our solar system. This small, icy moon appeared unremarkable in early observations, just another frozen satellite reflecting Saturn's pale light. But when the Cassini spacecraft flew close enough to study Enceladus in detail, it discovered one of the most remarkable phenomena in our solar system. From the south polar region of Enceladus, massive geysers of water vapor and ice particles erupt into space with such violence that they create one of Saturn's outer rings. These aren't gentle springs of water vapor, but powerful eruptions that shoot material hundreds of kilometers above the moon's surface at speeds of over 2,000 kilometers per hour. The energy required to drive these geysers comes from tidal heating caused by Saturn's immense gravitational field, which flexes and kneads Enceladus's interior like a cosmic stress ball. These geysers provide a direct window into Enceladus's interior, and what scientists have found there has profound implications for astrobiology. The water vapor contains complex organic molecules, including some that are essential precursors to life. More significantly, the chemical composition of these eruptions suggests that Enceladus harbors a global ocean beneath its icy shell, and that this ocean is in contact with a rocky seafloor where hydrothermal chemistry could create environments similar to Earth's deep-sea volcanic vents. The implications are staggering. On Earth, hydrothermal vents support some of the most extreme and diverse ecosystems on our planet, thriving in conditions that were once thought to be completely hostile to life. These environments don't depend on sunlight for energy, instead deriving power from chemical reactions between water and rock. If similar processes are occurring in Enceladus's hidden ocean, this small moon could harbor an entire biosphere completely independent of the sun's energy. What makes Enceladus even more intriguing is its geological activity despite its small size. Moons this small should have frozen solid billions of years ago, becoming geologically dead worlds covered in ancient impact craters. Instead, Enceladus displays a surface that's remarkably young and active, with vast regions that show clear signs of recent geological processes. The southern hemisphere is crisscrossed with what scientists call tiger stripes, massive cracks in the ice that serve as conduits for the spectacular geysers. These tiger stripes reveal a moon in constant motion, with tidal forces from Saturn continuously reshaping the interior and driving geological processes that keep Enceladus warm and active. The entire south polar region appears to be warmer than it should be, based on solar heating alone, suggesting that internal processes are generating significant amounts of heat. This creates a feedback loop where tidal heating drives geological activity, which in turn maintains the subsurface ocean that makes the geological activity possible. The discovery of active geology on Enceladus has forced scientists to reconsider their assumptions about habitability throughout the solar system. If a moon as small as Enceladus can maintain liquid water and active chemistry, then potentially habitable environments might exist throughout the outer solar system, wherever similar tidal heating mechanisms operate. This has expanded the concept of the habitable zone from a narrow band around the Sun to include regions far beyond what we previously considered capable of supporting life. Beyond these headline-grabbing moons, Saturn's family dozens includes of other worlds, each with its own unique characteristics and mysteries. Iapetus displays a bizarre two-toned coloration that makes it look like a cosmic yin-yang symbol, with one hemisphere as bright as snow and the other as dark as charcoal. This moon also features an equatorial ridge that runs nearly 3/4 of the way around its circumference, giving it the appearance of a walnut floating through space. Mimas bears the scars of a collision so violent it nearly destroyed the entire moon. The massive Herschel crater dominates one hemisphere, creating a striking resemblance to the Death Star from science fiction. This impact was so powerful that it created fractures on the opposite side of the moon, demonstrating the incredible forces involved in cosmic collisions. Each of these moons tells part of the larger story of Saturn's evolution and the dynamic processes that have shaped this corner of our solar system. Their diverse characteristics result from complex interactions between gravitational forces, tidal heating, impact events, and chemical processes that have been operating for billions of years. Together, they form a natural laboratory for studying planetary formation, geological processes, and the potential for life under extreme conditions. The gravitational relationships between Saturn's moons create resonances that maintain stable orbits while driving geological activity throughout the system. Some moons shepherd ring particles into narrow bands, while others create gaps and waves in the rings through their gravitational influence. This intricate dance of moons and rings creates a system of incredible complexity and beauty that continues to reveal new secrets with each passing year of observation and exploration. As we continue our journey through Saturn's hidden mysteries, we're beginning to understand that this distant world represents far more than a simple gas giant with pretty rings. Saturn and its moons form a complete planetary system that may harbor multiple forms of life and certainly contains environments unlike anything else in our solar system. The secrets waiting to be discovered in this alien realm could fundamentally change our understanding of life, geology, and planetary evolution throughout the universe. But Saturn's most profound secrets aren't written in its rings or carved into the surfaces of its moons. They're hidden within the planet's own mysterious interior, where pressures and temperatures create conditions so extreme they challenge the very foundations of our understanding of matter itself. What your teachers never explained is that Saturn is essentially a massive laboratory for exotic physics, where the familiar rules of chemistry and thermodynamics break down and give way to phenomena that seem more like magic than science. Deep within Saturn's churning atmosphere, beneath layers of hydrogen and helium clouds that stretch for thousands of kilometers, lies a realm where the distinction between liquid and gas begins to blur. As you descend deeper into Saturn's interior, the atmospheric pressure increases exponentially, eventually reaching levels that would crush any earthly material into powder. Under these conditions, hydrogen, the simplest and most abundant element in the universe, begins to transform into states of matter that don't exist anywhere on Earth's surface. Scientists believe that approximately halfway to Saturn's core, the pressure becomes so intense that hydrogen atoms are stripped of their electrons and compressed into a metallic state. This metallic hydrogen exists as a vast ocean of electrically conductive fluid that generates Saturn's powerful magnetic field through convection currents driven by the planet's rapid rotation. This hidden sea of exotic matter may extend for thousands of kilometers in all directions, creating an environment where electricity flows like water and magnetic fields shape the flow of matter on scales that dwarf entire continents. The temperatures within this metallic hydrogen ocean exceed 10,000 degrees Celsius, yet the extreme pressure prevents it from behaving like the gas we know on Earth's surface. Instead, it exists in a state that's neither solid nor liquid nor gas, but something entirely alien to our everyday experience. The energy contained within this hidden realm is almost incomprehensible, generated by the slow gravitational collapse of Saturn's massive bulk and the radioactive decay of heavy elements within the planet's core. Even more extraordinary is what scientists believe happens in the deepest regions of Saturn's atmosphere, where pressure and temperature reach truly staggering levels. Under these conditions, carbon atoms torn from methane molecules may be compressed and heated until they crystallize into diamonds. These aren't the small, precious gems we find on Earth, but massive diamond formations that could be kilometers across. These cosmic jewels rain down through Saturn's interior like glittering snow, eventually settling into the planet's core, where they form diamond mountains and valleys in a landscape no human will ever see. The physics of diamond formation within Saturn operates on scales that boggle the imagination. Each diamond raindrop begins as carbon atoms floating freely in the crushing depths of Saturn's atmosphere. As these atoms encounter the extreme conditions deep within the planet, they bond together in the precise crystalline structure that creates diamonds' incredible hardness and brilliance. But unlike Earth's diamonds, which form slowly over millions of years deep within our planet's crust, Saturn's diamonds are created continuously in a process that has been operating for billions of years. These diamond storms don't just create pretty crystals, they play a crucial role in Saturn's internal heat budget and magnetic field generation. As diamond particles sink towards Saturn's core, they release gravitational potential energy that contributes to the planet's internal heat production. This process helps explain why Saturn radiates more energy into space than it receives from the Sun, a phenomenon that has puzzled astronomers since it was first discovered decades ago. The core of Saturn itself represents one of the most mysterious objects in our solar system. Buried beneath thousands of kilometers of exotic atmosphere and metallic hydrogen ocean, Saturn's core exists under conditions so extreme that our most sophisticated computer models struggle to predict its properties accurately. Scientists believe the core is composed of rock, ice, and metallic compounds compressed to densities that exceed anything found on Earth's surface. The pressure at Saturn's center may be 10 million times greater than atmospheric pressure on Earth, while temperatures could reach 12,000 degrees Celsius, hotter than the surface of the Sun. Under these incredible conditions, the familiar elements that make up rocky planets behave in ways that defy our everyday understanding of chemistry. Silicon and oxygen, the building blocks of rock and sand on Earth, may exist in crystalline structures that have never been seen in terrestrial laboratories. Iron and nickel could form alloys with properties that would revolutionize materials science if we could somehow recreate them under earthly conditions. The very concept of solid and liquid becomes meaningless when matter is compressed to such extreme densities. What makes Saturn's interior even more fascinating is how it influences the planet's magnetic field and radiation environment. The convection currents within Saturn's metallic hydrogen ocean create a magnetic field that extends far beyond the planet's visible atmosphere, forming a vast magnetosphere that traps charged particles from the solar wind. This magnetic cocoon creates radiation belts that would be instantly lethal to any unprotected human visitor. Yet it also generates some of the most spectacular auroras in our solar system. Saturn's auroras are unlike anything seen on Earth. extending across thousands of kilometers and generating radio emissions that can be detected from Earth using relatively simple equipment. These cosmic light shows are powered by the same metallic hydrogen ocean that generates Saturn's magnetic field, creating a direct connection between the planet's hidden interior and the spectacular phenomena visible at its poles. When solar wind particles interact with Saturn's magnetosphere, they create displays of light that would dwarf Earth's northern lights, painting Saturn's polar regions with curtains of luminescence that dance across the planet's cloud tops. But perhaps the most mind-bending aspect of Saturn's interior is how it challenges our understanding of planetary formation itself. Traditional models suggest that gas giants like Saturn form through a process called core accretion, where a solid planetary core grows large enough to gravitationally capture massive amounts of hydrogen and helium from the surrounding nebula. However, recent computer simulations and observations from the Cassini spacecraft suggest that Saturn's formation may have been far more violent and chaotic than previously imagined. Some scientists now believe that Saturn may have experienced a massive collision with another planet-sized object early in its history, an event that would have completely disrupted its internal structure and mixed materials that should have remained separated. This collision hypothesis could explain several puzzling aspects of Saturn's current properties, including the unusual composition of its rings and the peculiar tilt of its magnetic field relative to its rotation axis. If this collision scenario is correct, it means that Saturn, as we know it today, is essentially a rebuilt planet, reassembled from the debris of a cosmic catastrophe that occurred billions of years ago. The metallic hydrogen ocean, the diamond rain, and the mysterious core would all be products of this violent restructuring process, creating a world that's fundamentally different from what it would have been if it had formed peacefully through gradual accretion. This collision hypothesis also has profound implications for our understanding of planetary system formation throughout the galaxy. If violent collisions between planet-sized objects were common in the early solar system, then similar processes may have occurred around other stars, creating gas giants with internal structures and properties that differ dramatically from current theoretical predictions. Saturn may not be unique in its bizarre internal composition, but rather representative of a common class of planets that formed through catastrophic restructuring rather than gradual assembly. The implications extend beyond planetary science into the realm of astrobiology and the search for life beyond Earth. The extreme conditions within Saturn's interior create chemical environments that could potentially support forms of life so alien that we lack the vocabulary to describe them. While traditional biology requires liquid water and relatively moderate temperatures, some scientists speculate that life could potentially emerge in the high-pressure, high-temperature environment of metallic hydrogen, using completely different chemistry and energy sources than anything found on Earth. These hypothetical organisms would exist in a realm where the very concepts of solid and liquid break down, where electrical conductivity creates opportunities for information storage and processing that have no earthly analog. They might derive energy from the radioactive decay of heavy elements, or from the chemical gradients created by Saturn's ongoing gravitational collapse. Such life forms would be so fundamentally different from terrestrial biology that we might not even recognize them as living organisms if we encountered them. The study of Saturn's interior also provides crucial insights into the formation and evolution of our solar system as a whole. The planet's current structure preserves evidence of the conditions that existed in the solar nebula billions of years ago, when the Sun and planets were first forming from a disk of gas and dust. By understanding how Saturn's interior evolved over time, scientists can piece together the history of planetary migration, collision events, and chemical processes that shape the architecture of our planetary system. Recent discoveries have revealed that Saturn's influence on solar system evolution extends far beyond its immediate neighborhood. Computer simulations suggest that Saturn's gravitational interactions with Jupiter may have caused both planets to migrate inward toward the Sun before being pulled back out to their current orbits. This migration process, known as the Grand Tack model, could explain many puzzling aspects of our solar system's structure, including why Mars is so much smaller than Earth, and why the asteroid belt contains such a diverse mixture of rocky and icy bodies. The hidden forces operating within Saturn's interior continue to shape the planet's evolution today. The ongoing gravitational collapse that powers the metallic hydrogen ocean also drives the planet's gradual cooling and contraction. Over billions of years, this process will fundamentally alter Saturn's structure, potentially changing the properties of its magnetic field, the behavior of its atmospheric dynamics, and even the stability of its spectacular ring system. As we drift deeper into contemplation of Saturn's hidden mysteries, we begin to appreciate that this distant world represents far more than a beautiful curiosity in our night sky. Saturn is a natural laboratory where the most extreme conditions in our solar system create phenomena that challenge our understanding of physics, chemistry, and planetary science. The secrets locked within its interior may hold keys to understanding not just the formation of our own solar system, but the processes that create and shape planetary systems throughout the galaxy. The diamond rain, the metallic hydrogen ocean, and the mysterious core represent just the beginning of what we're learning about this extraordinary world. Each new discovery reveals additional layers of complexity and wonder, reminding us that even in our own cosmic neighborhood, there are phenomena so alien and extraordinary that they stretch the boundaries of human imagination and scientific understanding. Yet Saturn's influence on our understanding of physics extends even further into realms that seem to blur the line between science and science fiction. What your teachers never mentioned is that Saturn generates more energy than it receives from the Sun, making it essentially a failed star that continues to glow with the heat of its own formation. This internal energy source creates atmospheric phenomena so bizarre that they challenge our most fundamental assumptions about weather and climate. The storms that rage across Saturn's surface operate on scales that dwarf anything found on Earth. The planet's most famous atmospheric feature, a massive hexagonal storm at its north pole, represents one of the most geometrically perfect structures found anywhere in nature. This hexagon is larger than two Earths placed side by side, with each of its 6 sides stretching across distances that would span entire continents on our planet. The precision of this geometric formation seems almost artificial, as if some cosmic architect had drawn it with a celestial compass and straight edge. What makes this hexagonal storm even more extraordinary is its stability. While hurricanes on Earth last for days or weeks at most, Saturn's hexagon has been raging for at least several decades, possibly much longer. The storm maintains its precise geometric shape despite the chaotic turbulence of Saturn's atmosphere, suggesting that deep physical principles govern its formation and persistence. Scientists believe the hexagon results from the interaction of jet streams moving at different speeds, creating standing wave patterns that naturally organize into this 6-sided structure. But the hexagon is just one example of Saturn's atmospheric mysteries. The planet's rapid rotation and internal heat source combine to create weather patterns that operate on timescales completely unlike anything in our terrestrial experience. Some of Saturn's storms persist for decades, slowly drifting across the planet's cloud tops while maintaining their intensity and structure. Others appear suddenly, grow to continental proportions within days, then disappear just as quickly, leaving scientists scrambling to understand the mechanisms that drive such dramatic changes. The colors that paint Saturn's atmospheric bands tell stories of chemical processes occurring at different altitudes and temperatures throughout the planet's atmosphere. The pale gold and beige hues that dominate Saturn's appearance result from complex organic compounds created when sunlight interacts with methane and ammonia in the planet's upper atmosphere. These photochemical reactions produce molecules called tholins, the same compounds that give Titan its orange coloration, and that may have played a crucial role in the development of life on early Earth. Deep within Saturn's atmosphere, where sunlight never penetrates, different chemical processes create their own palette of colors and compounds. The extreme pressures and temperatures in these hidden regions drive reactions that would be impossible under earthly conditions, potentially creating exotic materials that exist nowhere else in our solar system. Some of these deep atmospheric layers may contain compounds that could revolutionize chemistry and materials science if we could somehow study them directly. Saturn's atmospheric composition also reveals clues about the planet's formation and early evolution. The ratios of different elements and isotopes preserved in Saturn's atmosphere provide a chemical fingerprint of the solar nebula from which the planet formed billions of years ago. By studying these atmospheric signatures, scientists can piece together the conditions that existed in the early solar system and understand how planets like Saturn assembled from the primordial disk of gas and dust surrounding the young sun. The planet's helium abundance presents a particularly intriguing puzzle. Saturn contains less helium in its atmosphere than expected based on current models of planetary formation, suggesting that helium may be slowly separating from hydrogen and sinking toward the planet's core. This helium rain hypothesis could explain both Saturn's internal heat production and the gradual changes observed in its atmospheric composition over decades of observation. This process of helium differentiation represents another example of how Saturn continues to evolve billions of years after its formation. The planet is not a static object frozen in time, but a dynamic world where ongoing physical and chemical processes continuously reshape its structure and properties. The helium that rains into Saturn's interior carries with it traces of other potential elements, creating layers within the planet's deep atmosphere that are enriched in heavy elements and exotic compounds. The implications of these ongoing evolutionary processes extend far beyond Saturn itself. If helium differentiation is occurring in Saturn, similar processes may be happening in other gas giant planets throughout the galaxy. This could mean that the atmospheric compositions of giant planets change significantly over their lifetimes, making it difficult to understand their formation histories based on current observations alone. Saturn's magnetic field adds another layer of complexity to this already extraordinary world. Unlike Earth's relatively simple dipolar magnetic field, Saturn's magnetosphere exhibits unusual properties that have puzzled scientists since its discovery. The planet's magnetic field is remarkably well aligned with its rotation axis, much more so than any other planet in our solar system. This near-perfect alignment suggests that Saturn's magnetic field generation process differs fundamentally from the dynamo mechanisms operating in other worlds. The interaction between Saturn's magnetic field and its rings creates phenomena that exist nowhere else in our solar system. Charged particles trapped in Saturn's magnetosphere bombard the ring material continuously, causing chemical changes and creating faint auroral displays within the rings themselves. These ring auroras represent a completely unique form of atmospheric phenomenon, where electromagnetic processes create light displays in environments that are neither truly solid nor gaseous. Saturn's magnetosphere also plays a crucial role in shaping the evolution of its moons. The magnetic field channels charge particles from the solar wind into specific regions around Saturn, creating radiation environments that vary dramatically depending on orbital location. Moons that orbit within Saturn's intense radiation belts experience continuous bombardment that alters their surface chemistry and may drive geological processes through radiolytic heating. The seasonal changes that occur throughout Saturn's long year add yet another dimension to the planet's complexity. Because Saturn's axis is tilted at an angle similar to Earth's, different regions of the planet experience dramatic seasonal variations as it orbits the Sun. However, Saturn's seasons last approximately 7 Earth years each, creating climate patterns that operate on timescales completely unlike anything in our terrestrial experience. During Saturn's long northern summer, the continuous sunlight falling on the planet's north polar region drives atmospheric circulation patterns that can be observed from Earth. The hexagonal storm becomes more pronounced and active, while the overall atmospheric dynamics shift in response to the changing patterns of solar heating. These seasonal changes provide a natural experiment for understanding how atmospheric systems respond to long-term variations in energy input. The infrared radiation emitted by Saturn tells its own story of internal heat distribution and atmospheric dynamics. Different regions of the planet radiate different amounts of heat, creating a thermal map that reveals the hidden circulation patterns within Saturn's deep atmosphere. Some regions appear surprisingly warm, suggesting the presence of atmospheric motions that transport heat from the planet's interior to its visible cloud layers. These thermal signatures also reveal the presence of atmospheric phenomena that remain invisible to optical telescopes. Deep convection cells transport material vertically through Saturn's atmosphere, creating temperature variations that can be detected by sensitive infrared instruments. These convection patterns may play a crucial role in maintaining Saturn's atmospheric circulation and could influence the formation and evolution of the planet's spectacular storm systems. The study of Saturn's thermal properties has also revealed unexpected connections between the planet's interior and its magnetic field generation. Variations in heat flow from different regions of Saturn's interior may influence the convection patterns within the metallic hydrogen ocean, potentially affecting the strength and structure of the planet's magnetic field over long timescales. Perhaps most remarkably, recent observations have suggested that Saturn's internal structure may be far more complex than previously imagined. Instead of consisting of distinct layers with sharp boundaries, Saturn's interior may be characterized by gradual transitions and partially mixed regions that create a fuzzy core extending far into what was once thought to be purely atmospheric material. This fuzzy core model has profound implications for our understanding of how giant planets form and evolve. If Saturn's rock and ice components are distributed throughout a large fraction of the planet's interior rather than concentrated in a small central core, it suggests that the planet's formation involved processes that thoroughly mixed materials from different regions of the early solar system. The gravitational field measurements made by the Cassini spacecraft during its final plunges into Saturn's atmosphere have provided the most detailed information yet about the planet's internal mass distribution. These observations reveal that Saturn's interior is neither fully mixed nor completely differentiated, but exists in an intermediate state that reflects the complex history of the planet's formation and evolution. As we continue to unravel Saturn's mysteries, each new discovery reveals additional layers of complexity that challenge our understanding of planetary physics and formation processes. This distant world serves as a natural laboratory for studying extreme states of matter, atmospheric dynamics, and magnetic field generation under conditions that cannot be replicated in any earthly laboratory. The secrets that Saturn continues to reveal remind us that even within our own solar system, There are phenomena so extraordinary and alien that they expand our conception of what's possible in the universe. Every observation, every measurement, every new piece of data adds another thread to the tapestry of knowledge we're weaving about this remarkable world and its place in the cosmic story that connects us all. The mysteries hidden within Saturn's gravitational embrace extend far beyond what we can observe directly, reaching into realms where space and time themselves become fluid concepts that dance to the rhythm of cosmic forces. What your teachers never shared with you is that Saturn exists at the center of gravitational interactions so complex, they influence the behavior of objects billions of kilometers away, creating ripples through space-time that have been shaping our solar system for eons. The gravitational field that Saturn generates is not uniform or simple, but rather a complex three-dimensional sculpture carved by the planet's rotation, internal mass distribution, and the constant gravitational tugging of its many moons. This field creates what scientists call gravitational resonances, invisible highways through space where small objects naturally accumulate or are systematically expelled, depending on the precise mathematics of their orbital periods. These work like cosmic clockwork, with periods that are exact mathematical ratios of each other. When a particle or small moon orbits Saturn at just the right distance, it experiences a gentle but persistent gravitational nudge from one of Saturn's larger moons at precisely the same point in each orbit. Over millions of years, these tiny nudges accumulate into dramatic changes in orbital behavior, either shepherding objects into stable configurations or ejecting them from the Saturn system entirely. The most spectacular example of this gravitational choreography can be found in the gaps within Saturn's rings. The Cassini division, a prominent dark band that separates Saturn's A and B rings, exists because any particle that tries to orbit in that region experiences a gravitational resonance with the moon Mimas that gradually removes it from that location. It's as if an invisible cosmic broom continuously sweeps that region clean, maintaining a gap that has persisted for millions of years. But resonances don't just create empty spaces. They also concentrate material into incredibly precise structures. Some of Saturn's narrow ringlets are maintained by resonances that act like gravitational corrals, keeping particles confined to paths only a few kilometers wide, despite the chaotic environment of the ring system. These structures demonstrate the extraordinary precision with which gravitational forces can organize matter across vast distances of space. The mathematical beauty of these resonances reflects deeper principles about how gravity shapes structures throughout the universe. The same gravitational harmonics that create patterns in Saturn's rings also organize asteroid belts around other stars, shape the distribution of galaxies across cosmic distances, and even influence the orbits of planets around distant suns. Saturn serves as a natural laboratory where we can observe these fundamental processes in exquisite detail. What makes Saturn's gravitational environment even more remarkable is how it has evolved over billions of years. The positions and masses of Saturn's moons have changed throughout the planet's history, causing the locations and strengths of gravitational resonances to shift accordingly. This means that the ring structures we see today are not the same as those that existed when life first emerged on Earth. The rings have been continuously reshaped by the slowly changing gravitational landscape of the Saturn system. Recent computer simulations have revealed that some of Saturn's moons may have migrated outward from the planet over geological time, driven by tidal interactions that gradually transfer energy from Saturn's rotation to the moon's orbital motion. As these moons moved outward, they swept through the ring system like cosmic bulldozers, potentially destroying and reforming ring structures multiple times throughout Saturn's history. This migration process may explain some of the most puzzling aspects of Saturn's current configuration. The precise alignment of certain ring features with specific moon orbits suggests that these structures formed relatively recently, when the moons reached their current positions. This implies that Saturn's rings may be much younger than the planet itself, perhaps created by catastrophic events that occurred within the last few 100 million years. The tidal forces that drive this orbital evolution operate through mechanisms so subtle they were only recently understood by planetary scientists. As Saturn's moons orbit the planet, they create tiny bulges in Saturn's shape through gravitational attraction. These bulges lag slightly behind the moons due to Saturn's internal friction, creating a gravitational torque that gradually increases the moon's orbital energy and causes them to spiral outward. This same tidal mechanism explains how some of Saturn's moons maintain geological activity despite their small sizes and great distances from the Sun. The constant flexing caused by tidal forces generates internal heat through friction, keeping subsurface oceans liquid and driving geological processes that would otherwise have ceased billions of years ago. It's a cosmic heating system powered by the dance of gravity itself. The precision required to maintain these tidal heating mechanisms reveals the extraordinary stability of Saturn's gravitational environment. Even tiny changes in orbital periods or planetary rotation rates could disrupt the delicate balance that keeps moons like Enceladus geologically active. This stability suggests that Saturn's system has reached a kind of gravitational equilibrium that has persisted for hundreds of millions of years. But perhaps the most mind-bending aspect of Saturn's gravitational influence is how it extends far beyond the planet's immediate vicinity to shape the evolution of our entire solar system. Saturn's massive gravitational field has acted as a cosmic shepherd, herding asteroids and comets into specific orbital configurations while protecting the inner solar system from bombardment by dangerous objects. The gravitational partnership between Saturn and Jupiter creates what astronomers call the asteroid belt, a region of space between Mars and Jupiter where rocky debris has accumulated over billions of years. Without Saturn's gravitational influence, this material might have coalesced into another planet or been scattered throughout the solar system, potentially preventing Earth from developing the stable conditions necessary for complex life to emerge. Computer simulations of solar system formation reveal that Saturn's current orbit represents a delicate balance between competing gravitational forces. If Saturn had formed slightly closer to the Sun, or with a different mass, its gravitational influence could have destabilized the orbits of the inner planets, potentially ejecting Earth from the solar system or sending it spiraling into the Sun. This realization has profound implications for understanding planetary systems around other stars. The presence of a Saturn-like planet in the right location may be crucial for maintaining the orbital stability necessary for habitable worlds to exist over the billions of years required for complex life to evolve. Saturn may just not be a beautiful ornament in our night sky, but an essential guardian that has made our existence possible. The gravitational waves generated by Saturn's motion through space-time represent another frontier in our understanding of this remarkable world. While these waves are far too weak to detect with current technology, they carry information about Saturn's internal structure and rotational dynamics that could revolutionize our understanding of the planet's composition and evolution. Future gravitational wave detectors may be sensitive enough to measure the tiny space-time distortions created by Saturn's rotation and orbital motion, providing unprecedented insights into the planet's interior structure. These measurements could reveal whether Saturn's core is solid or liquid, how its internal mass is distributed, and how its interior has evolved since the planet's formation. The concept that Saturn continuously generates gravitational waves simply by existing and moving through space represents a beautiful connection between this ancient world and cutting-edge physics. Every rotation of Saturn, every orbital motion of its moons, every circulation pattern in its atmosphere creates ripples in space-time that propagate outward at the speed of light, carrying information about these processes to distant observers. These gravitational signatures also provide a new way to search for similar planets around other stars. The gravitational waves generated by giant planets could potentially be detected across interstellar distances, revealing the presence of Saturn-like worlds that are too faint to observe directly with optical telescopes. Saturn may serve as a template for understanding an entire class of planets that exist throughout the galaxy. The magnetic interactions between Saturn and its moons create additional layers of complexity that challenge our understanding of electromagnetic processes in space. Some of Saturn's moons orbit within the planet's magnetic field, creating electrical circuits that span thousands of kilometers and generate radio emissions detectable from Earth. The Moon, Io, creates a similar electromagnetic connection with Jupiter, but Saturn's interactions with its moons operate under different conditions that produce unique phenomena. The electrical currents flowing between Saturn and some of its moons may influence atmospheric processes on both the planet and the moons, creating feedback loops that connect electromagnetic and gravitational processes across the entire Saturn system. These electromagnetic interactions also affect the behavior of charged particles in Saturn's magnetosphere, creating radiation environments that vary dramatically depending on location and time. The complex interplay between magnetic fields, gravitational forces, and charged particle motion creates a natural plasma physics laboratory where processes important for understanding stellar atmospheres and galactic magnetic fields can be studied in detail. The seasonal variations in Saturn's magnetic field strength and configuration add another dimension to these electromagnetic phenomena. As different regions of Saturn receive varying amounts of solar radiation throughout the planet's long year, the resulting changes in atmospheric circulation affect the generation of the magnetic field itself, creating feedback loops that connect electromagnetic processes to atmospheric dynamics. Recent observations have revealed that Saturn's magnetic field exhibits fluctuations on timescales ranging from minutes to years, suggesting that the underlying dynamo process in the planet's interior is far more complex and variable than previously imagined. These magnetic field variations may influence everything from the behavior of Saturn's rings to the atmospheric dynamics of its moons. The study of these magnetic field fluctuations provides insights into the fundamental physics of dynamo processes that operate in planets, stars, and galaxies throughout the universe. Saturn's magnetic field serves as a natural laboratory for testing theories about how rotating, electrically conducting fluids generate and maintain magnetic fields over astronomical timescales. As we drift deeper into contemplation of Saturn's gravitational and electromagnetic mysteries, we begin to appreciate that this distant world represents a nexus of physical processes that connect the smallest scales of plasma physics to the largest scales of galactic dynamics. The forces at work within and around Saturn operate according to the same fundamental principles that govern the behavior of matter and energy throughout the cosmos. The invisible threads of gravity and magnetism that bind Saturn's system together also weave through the fabric of space-time itself, creating connections that span from the quantum realm to the cosmic web of galaxies. In studying Saturn, we're not just learning about a single planet, but gaining insights into the fundamental forces that shape the universe at every scale. Every measurement we make of Saturn's gravitational field, every observation of its magnetic environment, Every detection of electromagnetic emissions from its magnetosphere adds another piece to the vast puzzle of cosmic evolution. These seemingly abstract physical processes have practical implications that reach across billions of years of time and vast distances of space. The gravitational resonances that organize Saturn's rings operate according to the same mathematical principles that determine the orbits of planets around distant stars. The tidal heating that drives geological activity on Saturn's moons may be creating habitable environments around gas giant planets throughout the galaxy. The electromagnetic processes that generate Saturn's auroras could influence the atmospheric chemistry of countless worlds orbiting other suns. In this way, Saturn serves as both a unique individual world and a representative example of processes that may be common throughout the universe. The planet's extraordinary properties result from the same fundamental forces that govern all matter and energy, operating under the specific conditions created by Saturn's mass, composition, rotation, and orbital environment. The ongoing evolution of Saturn's gravitational and electromagnetic environment ensures that this world will continue to reveal new secrets for generations of future scientists to discover. As the planet's moons slowly migrate outward, as its magnetic field continues to fluctuate, as its rings evolve and change, Saturn remains a dynamic laboratory where cosmic forces continue to create new phenomena and new opportunities for understanding. The hidden gravitational architecture that shapes Saturn's domain extends its influence across space and time in ways that connect this ancient world to the deepest mysteries of cosmic evolution. In contemplating these invisible forces, we touch something profound about the nature of existence itself and our place within the grand symphony of gravitational and electromagnetic interactions that bind the universe together. As we continue our journey through Saturn's secrets, we find ourselves drawn ever deeper into mysteries that blur the boundaries between physics and philosophy, between the observable and the unknowable, between the ancient past and the far future of cosmic evolution. Saturn waits patiently in the darkness, continuing to spin its gravitational and electromagnetic web, weaving connections that span from the quantum foam to the cosmic horizon, inviting us to discover ever more profound truths about the universe we call home. The electromagnetic phenomena surrounding Saturn create a cosmic symphony that resonates through frequencies no human ear was designed to perceive. Yet these invisible melodies carry secrets about the fundamental nature of matter and energy that govern not just this distant world, but the entire universe. What your teachers never revealed is that Saturn exists within a bubble of electromagnetic activity so intense and complex that it essentially creates its own pocket dimension of space, where the normal rules of physics bend and twist into configurations that challenge our deepest understanding of reality itself. The radio emissions generated by Saturn's magnetosphere tell stories of particle interactions occurring on scales that dwarf entire continents. These electromagnetic signals pulse and vary with rhythms that seem almost biological, as if the planet itself were breathing through wavelengths of radio energy that stretch across millions of kilometers of space. When scientists first detected these emissions, they were startled to discover that Saturn's electromagnetic voice changes with the seasons, growing stronger and more complex as different regions of the planet receive varying amounts of solar energy throughout its long orbital journey. The source of these radio emissions lies in the complex dance between charged particles trapped within Saturn's magnetosphere and the planet's rapidly rotating magnetic field. As these particles spiral along magnetic field lines, they generate electromagnetic radiation through a process called synchrotron emission, creating radio waves that carry the signature of Saturn's internal magnetic environment across the solar system. These signals provide a direct window into processes occurring deep within Saturn's metallic hydrogen ocean, where convection currents generate the magnetic field that shapes the electromagnetic environment throughout the entire Saturn system. But perhaps the most extraordinary aspect of Saturn's electromagnetic environment is how it creates auroral displays that dwarf anything seen on Earth. Saturn's auroras extend across thousands of square kilometers at each pole, generating ultraviolet and infrared radiation so intense it would be visible to the naked eye if human vision could perceive those wavelengths. These cosmic light shows are powered by the interaction between Saturn's magnetic field and charged particles streaming from the Sun. But they're also influenced by electromagnetic processes occurring within Saturn's rings and on the surfaces of its major moons. The auroral displays at Saturn's poles operate according to physical principles that reveal deep connections between electromagnetic theory and plasma physics. As charged particles from the solar wind encounter Saturn's magnetic field, they're channeled along magnetic field lines toward the planet's polar regions, where they collide with atoms and molecules in Saturn's upper atmosphere. These collisions excite the atmospheric gases, causing them to emit light in specific wavelengths that create the spectacular auroral curtains that dance across Saturn's polar skies. What makes Saturn's auroras unique is their persistence and structure. Unlike Earth's auroras, which typically appear as shimmering curtains or arcs of light, Saturn's auroral displays often form precise geometric patterns that mirror the structure of the planet's magnetic field. Some auroral features maintain their shape and intensity for days or weeks, suggesting that they're controlled by stable magnetic field configurations that have persisted within Saturn's magnetosphere for extended periods. The electromagnetic environment around Saturn also creates phenomena that exist nowhere else in our solar system. The interaction between the planet's magnetic field and its rings generates what scientists call spokes, mysterious radial features that appear and disappear in the rings with clockwork regularity. These spokes form when electromagnetic forces temporarily lift tiny dust particles above the ring plane, creating shadows that sweep across the rings like the hands of a cosmic timepiece. The physics behind spoke formation involves electromagnetic forces that operate on scales ranging from individual dust grains to structures hundreds of kilometers across. When Saturn's magnetic field interacts with charged dust particles in the rings, it can overcome the gravitational forces that normally keep these particles confined to the ring plane. The result is a temporary levitation effect that creates the ghostly spokes, which then fade as the electromagnetic conditions change and gravity reasserts its influence. Recent observations have revealed that spoke activity varies with Saturn seasons and with changes in the solar wind environment around the planet. During periods of high solar activity, when the solar wind carries more charged particles and stronger magnetic fields, spoke formation increases dramatically. This suggests that Saturn's rings are constantly responding to electromagnetic conditions throughout the solar system, making them sensitive indicators of space weather processes that affect the entire outer solar system. The electromagnetic interactions between Saturn and its largest moon, Titan, create another layer of complexity in this already extraordinary system. Titan's thick atmosphere and surface lakes of liquid hydrocarbons interact with Saturn's magnetic field in ways that generate radio emissions and may drive atmospheric circulation patterns on the moon itself. As Titan orbits through different regions of Saturn's magnetosphere, the changing electromagnetic environment may influence weather patterns, atmospheric chemistry, and even geological processes on this alien world. These electromagnetic connections between Saturn and Titan represent a form of planetary satellite interaction that was unknown before the Cassini mission revealed their existence. The electrical currents that flow between Saturn and Titan create a circuit that spans hundreds of thousands of kilometers, carrying energy and information across the vacuum of space through electromagnetic fields. This cosmic electrical circuit may play a role in maintaining Titan's atmospheric composition and driving the complex organic chemistry that makes this moon one of the most Earth-like worlds in our solar system. The study of Saturn's electromagnetic environment has also revealed unexpected connections to fundamental physics and the behavior of matter under extreme conditions. The plasma physics processes that occur within Saturn's magnetosphere operate under conditions of temperature, density, and magnetic field strength that cannot be replicated in any terrestrial laboratory. These natural experiments provide insights into how matter behaves in environments similar to those found in stellar atmospheres, accretion disks around black holes, and the magnetic fields of neutron stars. The magnetic reconnection events that occur within Saturn's magnetosphere represent particularly violent examples of plasma physics in action. When magnetic field lines with opposite orientations encounter each other, they can suddenly reconfigure in explosive events that release enormous amounts of energy in fractions of a second. These magnetic explosions accelerate charged particles to incredible speeds and generate bursts of electromagnetic radiation that can be detected from Earth. Understanding magnetic reconnection at Saturn has implications that extend far beyond planetary science. Similar processes occur in the Sun's corona, where magnetic reconnection drives solar flares, and coronal mass ejections that can affect technological systems throughout the inner solar system. The magnetic reconnection events observed at Saturn provide a natural laboratory for studying these fundamental plasma physics processes under controlled conditions that would be impossible to create artificially. The electromagnetic properties of Saturn's interior add another dimension to these already complex phenomena. The convection currents within Saturn's metallic hydrogen ocean that generate the planet's magnetic field operate according to magnetohydrodynamic principles that govern the behavior of electrically conducting fluids in magnetic fields. These same principles control the behavior of plasma in fusion reactors, the dynamics of stellar interiors, and the formation of magnetic fields in galaxies throughout the universe. The precise mechanism by which Saturn generates its magnetic field remains one of the outstanding puzzles in planetary science. Unlike Earth's magnetic field, which is generated by convection in a liquid iron core, Saturn's magnetic field emerges from convection in metallic hydrogen under conditions of extreme pressure and temperature. The mathematical models that describe this process push the boundaries of our understanding of fluid dynamics and electromagnetic theory. Recent computer simulations of Saturn's magnetic field generation have revealed that the process may be far more complex and variable than previously imagined. The convection patterns within Saturn's metallic hydrogen ocean may undergo periodic reorganizations that dramatically alter the strength and structure of the magnetic field over timescales ranging from years to centuries. These magnetic field variations could have profound effects on Saturn's atmospheric dynamics, ring evolution, and the electromagnetic environment throughout the entire Saturn system. The electromagnetic signature of Saturn's rotation presents another fascinating puzzle that connects the planet's interior dynamics to its observable properties. Unlike most planets, Saturn's magnetic field rotates at almost exactly the same rate as the planet's deep interior, suggesting that the magnetic field generation process is somehow locked to the planet's rotation in ways that are not fully understood. This precise synchronization between magnetic field rotation and planetary rotation may result from feedback mechanisms that connect electromagnetic processes in the metallic hydrogen ocean to mechanical processes in the planet's solid core. The study of these electromagnetic phenomena at Saturn has revolutionized our understanding of how magnetic fields interact with rotating fluids under extreme conditions. The insights gained from studying Saturn's magnetosphere and interior dynamics have applications that extend from fusion energy research to understanding the magnetic fields of exoplanets orbiting distant stars. Saturn serves as a natural laboratory where we can observe electromagnetic processes that are fundamental to understanding how magnetic fields operate throughout the universe. The seasonal variations in Saturn's electromagnetic environment create additional opportunities to study how planetary magnetic fields respond to changing external conditions. As Saturn orbits the Sun, different regions of its magnetosphere receive varying amounts of solar wind input, creating natural experiments in how planetary magnetic fields adapt to changing boundary conditions. These seasonal changes provide insights into the fundamental stability and variability of planetary magnetic fields that cannot be obtained through short-term observations. The electromagnetic interactions between Saturn's various moons and the planet's magnetic field create a complex web of electrical currents and radio emissions that make the Saturn system one of the most electromagnetically active regions in our solar system. Each moon that orbits within Saturn's magnetosphere contributes to this electromagnetic symphony in its own unique way, depending on its size, composition, orbital position, and internal structure. The moon Enceladus, with its active water vapor geysers, creates particularly interesting electromagnetic phenomena as it orbits through Saturn's magnetic field. The water vapor and ice particles ejected from Enceladus's south polar region become ionized by solar radiation and Saturn's magnetic field, creating a plasma torus that extends around Enceladus's entire orbital path. This ionized material interacts with Saturn's magnetic field to generate radio emissions and may influence the behavior of charged particles throughout the inner Saturn system. These electromagnetic interactions between Saturn and its moons provide natural laboratories for studying plasma physics processes that are important for understanding how magnetic fields interact with atmospheric and surface materials throughout the solar system. Similar processes may occur around gas giant planets orbiting other stars, potentially creating electromagnetic signatures that could be detected by future radio telescopes designed to study exoplanetary systems. The radio emissions generated by Saturn's electromagnetic environment also provide a means of studying the planet's interior structure and dynamics through techniques similar to seismology on Earth. Just as seismic waves reveal the internal structure of our planet, electromagnetic waves generated within Saturn's interior carry information about the density, composition, and convection patterns within the metallic hydrogen ocean. By carefully analyzing the radio emissions from Saturn, scientists can probe the planet's interior structure in ways that would be impossible using gravitational measurements alone. The polarization characteristics of Saturn's radio emissions reveal additional details about the electromagnetic environment within the planet's magnetosphere. Different types of plasma waves generate radio emissions with distinct polarization signatures, allowing scientists to identify and study specific electromagnetic processes occurring at different locations field. These within Saturn's magnetic polarization measurements provide insights into the three-dimensional structure of Saturn's magnetosphere and how it changes in response to varying solar wind conditions. The discovery that Saturn's radio emissions exhibit periodicities that are slightly different from the planet's optical rotation period has led to new theories about how the planet's magnetic field is generated and maintained. These radio period variations suggest that the electromagnetic processes within Saturn's interior may operate according to timescales that are distinct from the planet's mechanical rotation, indicating complex feedback mechanisms between electromagnetic and fluid dynamical processes within the metallic hydrogen ocean. The electromagnetic environment around Saturn also influences the chemical evolution of the planet's rings and moons through radiation processing of surface materials. High-energy charged particles trapped within Saturn's magnetic field continuously bombard the surfaces of ring particles and moons, breaking apart molecules and creating new chemical compounds that would not exist under normal conditions. This radiation processing may be responsible for some of the color variations observed in Saturn's rings, and may play a role in the formation of complex organic molecules on some of Saturn's moons. The study of radiation processing at Saturn has implications for understanding how electromagnetic environments affect the chemical evolution of planetary surfaces throughout the solar system and around other stars. The same processes that alter the composition of Saturn's rings and moons may be occurring around gas giant planets in other planetary systems, potentially influencing the habitability and chemical complexity of worlds orbiting distant suns. As we continue to unravel the electromagnetic mysteries surrounding Saturn, each new discovery reveals additional connections between this distant world and fundamental processes that operate throughout the universe. The radio waves that carry Saturn's electromagnetic signature across the solar system also carry information about plasma physics, magnetic field generation, and electromagnetic interactions that are relevant to understanding everything from fusion energy to the behavior of matter in the most extreme environments in the cosmos. The invisible electromagnetic threads that bind Saturn's system together represent just one aspect of the complex web of forces and interactions that make this world one of the most fascinating and scientifically valuable objects in our solar system. As our instruments become more sensitive and our theoretical understanding more sophisticated, Saturn continues to reveal new electromagnetic phenomena that challenge our understanding of how planets, magnetic fields, and charged particles interact in the vast theater of space. The electromagnetic symphony that Saturn plays across the radio spectrum serves as a constant reminder that this ancient world remains dynamically active and full of surprises, continuing to generate new electromagnetic phenomena that will provide opportunities for discovery and understanding for generations of scientists yet to come. In listening to Saturn's radio voice, we hear echoes of fundamental physical processes that connect this distant planet to the deepest mysteries of cosmic evolution and the electromagnetic forces that shape the universe at every scale. The electromagnetic revelations surrounding Saturn pale in comparison to what awaits us when we venture into the realm of temporal mysteries that this ancient world harbors within its gravitational embrace. What your teachers never dared to whisper is that Saturn exists as a cosmic timekeeper, a celestial chronometer whose very existence challenges our most fundamental assumptions about the nature of time itself and how it flows through the fabric of our universe. Time near Saturn doesn't behave the way it does on Earth. The immense gravitational field generated by this massive world actually warps the flow of time itself, creating what Einstein predicted but few truly comprehend. If you could somehow stand on a platform just above Saturn's cloud tops, time would pass more slowly for you relative to someone watching from Earth. This isn't science fiction or theoretical speculation. It's a measurable physical reality that demonstrates how gravity doesn't just bend space, but bends time along with it. This gravitational time dilation effect becomes even more pronounced as you venture deeper into Saturn's gravitational well. Near the planets, where core gravitational forces reach their maximum intensity, time would crawl at a pace that seems almost frozen compared to the flow of time in the outer solar system. A single day spent in Saturn's deep interior would correspond to slightly more than a day experienced by distant observers, creating a temporal gradient that stretches across the planet's entire structure. The implications of this time dilation extend far beyond abstract physics. It means that different regions of Saturn's interior are literally aging at different rates. The metallic hydrogen ocean experiences time differently than the outer atmospheric layers. The core exists in its own temporal bubble, where seconds tick by at a pace distinct from the rhythm experienced by the rings high above. Saturn is not just a planet, it's a collection of temporal zones, each one experiencing the passage of time according to the intensity of gravitational forces at that location. This temporal complexity becomes even more fascinating when you consider Saturn's rotation. As the planet spins, different parts of its structure move at different velocities, creating additional time dilation effects due to the relativistic consequences of motion. The equatorial regions, spinning faster than the poles, experience time at a slightly different rate than the polar regions. The result is a planet where time itself becomes a three-dimensional landscape, varying not just with depth, but with latitude and the complex interplay of gravitational and rotational forces. The moons orbiting Saturn exist within their own unique temporal environments, each one experiencing time according to its distance from the planet and its orbital velocity. Mimas, orbiting close to Saturn, experiences time differently than distant Iapetus. This creates a natural hierarchy of temporal zones throughout the Saturn system, where each moon exists in its own pocket of space-time that ages according to the gravitational mathematics of its particular orbital configuration. These temporal effects have profound implications for understanding how Saturn's system has evolved over billions of years. Different components of the system have literally experienced different amounts of time since their formation, creating age gradients that influence everything from geological processes to orbital dynamics. The inner moons have experienced slightly less total time than the outer moons, creating subtle but measurable differences in their evolutionary histories. The study of time dilation at Saturn also provides insights into how temporal effects might influence planetary systems around other stars. Gas giant planets with masses similar to Saturn would create their own temporal landscapes, potentially affecting the evolution of life on nearby worlds in ways that are only beginning to be understood. The flow of time itself becomes a factor in planetary habitability, adding another layer of complexity to our understanding of how life might emerge and evolve throughout the galaxy. But Saturn's relationship with time extends beyond the relativistic effects of gravity and motion into realms that touch the very foundations of cosmic evolution. The planet serves as a repository of temporal information, preserving within its structure evidence of events that occurred billions of years ago during the formation of our solar system. The isotopic signatures locked within Saturn's atmosphere tell stories of stellar nucleosynthesis that occurred in stars that died before our sun was born, creating a temporal connection that spans multiple generations of stellar evolution. The helium abundance patterns within Saturn's interior carry information about the thermal history of the early solar system, when planets were still hot from their formation, and the sun was just beginning to settle into its current state of stable fusion. These chemical fingerprints provide a direct link to conditions that existed billions of years ago, making Saturn a kind of temporal archive that preserves evidence of cosmic events that shape the architecture of our planetary system. The rings of Saturn themselves represent a form of temporal phenomenon that operates on scales both vast and intimate. Each particle in the rings carries its own history, some potentially dating back to the formation of the Saturn system, others created by relatively recent collisions and disruptions. The rings exist in a state of constant renewal and destruction, creating a temporal cycle where ancient material is continuously recycled into new configurations through processes that have been operating for millions or possibly billions of years. The spoke formations that appear and disappear in Saturn's rings operate according to temporal rhythms that mirror the planet's rotation and magnetic field variations. These ephemeral structures form, persist for hours or days, then fade away, only to reform in new locations as electromagnetic conditions change throughout the Saturn system. The spokes represent a form of temporal pattern that emerges from the complex interaction between electromagnetic forces and ring particle dynamics, creating ghostly features that exist briefly before dissolving back into the ring material from which they emerged. The seasonal changes that occur throughout Saturn's long year create temporal cycles that span decades of Earth time. These extended seasons drive atmospheric changes, ring dynamics, and moon interactions according to rhythms that are completely unlike anything experienced on our rapidly rotating, closely orbiting world. Saturn's seasons unfold like a slow-motion ballet, with atmospheric patterns and electromagnetic phenomena evolving over timescales that challenge human perception and require decades of patient observation to fully understand. The aurora displays at Saturn's poles wax and wane according to temporal patterns that reflect the complex interplay between solar wind variations, seasonal changes, and internal magnetospheric dynamics. Some auroral features persist for weeks or months, while others flicker and dance on timescales of minutes or hours. This temporal variety in auroral behavior provides insights into the different physical processes that drive electromagnetic phenomena throughout the Saturn system. The gravitational interactions between Saturn's moons create temporal resonances that influence orbital evolution over millions of years. These gravitational harmonics operate like cosmic clockwork, with small periodic forces gradually accumulating over vast spans of time to produce dramatic changes in moon orbits, ring structure, and system stability. The temporal scales involved in these processes dwarf human history, yet their effects can be measured through careful observations of orbital mechanics and ring dynamics. The tidal heating that keeps some of Saturn's moons geologically active operates through temporal mechanisms that convert orbital energy into thermal energy over extended periods. The flexing and heating cycles that drive geological activity on moons like Enceladus operate according to temporal rhythms determined by orbital periods and gravitational interactions. These thermal cycles create geological activity that operates on timescales ranging from days to millions of years, depending on the specific processes involved. The evolution of Saturn's internal structure represents another temporal mystery that spans the entire history of the solar system. The ongoing differentiation of materials within Saturn's interior, the gradual cooling and contraction of the planet, and the slow changes in internal heat production all operate according to temporal scales that are measured in billions of years. These processes connect Saturn's current structure to its primordial formation and provide insights into how the planet will continue to evolve over cosmic time. The magnetic field generation within Saturn's metallic hydrogen ocean operates according to temporal dynamics that may vary on scales ranging from years to centuries. The convection patterns that drive the magnetic dynamo process respond to changes in internal heat production, rotation rate, and external boundary conditions, according to temporal rhythms that are only beginning to be understood. These magnetic field variations create temporal changes in the electromagnetic environment throughout the Saturn system. The chemical evolution of Saturn's atmosphere proceeds according to temporal processes that involve photochemistry, atmospheric circulation, and material exchange with the rings and moons. Some atmospheric constituents have lifetimes measured in hours or days, while others persist for decades or centuries. This creates a temporal hierarchy of chemical processes that operates simultaneously across multiple timescales, producing the complex atmospheric composition that characterizes Saturn's visible appearance. The impact history recorded in the surfaces of Saturn's moons provides a temporal record of bombardment events that spans billions of years. The crater populations on different moons tell stories of changing impact rates, migration of debris populations, and the gradual evolution of the outer solar system environment. This temporal record, preserved in crater statistics, provides insights into the dynamical history of the entire solar system. The organic chemistry occurring on Titan operates according to temporal processes that may be relevant to understanding the prebiotic chemistry that preceded the origin of life on Earth. The seasonal cycles of hydrocarbon precipitation and evaporation, the gradual accumulation of organic materials on the surface, and the chemical evolution of atmospheric constituents all proceed according to temporal rhythms that may provide insights into how complex organic chemistry develops over planetary timescales. The ongoing evolution of Saturn's ring system represents one of the most dynamic temporal processes in the solar system. The continuous creation and destruction of ring material, the migration of particles between different ring regions, and the formation and dissolution of temporary structures all occur according to temporal cycles that range from hours to millions of years. This temporal complexity makes Saturn's rings a natural laboratory for studying how gravitational and electromagnetic forces shape matter over multiple timescales. The observational history of Saturn itself provides a temporal perspective on how human understanding of planetary systems has evolved over centuries of astronomical investigation. From Galileo's first telescopic observations to the detailed measurements made by modern spacecraft, each generation of observers has added new temporal dimensions to our understanding of this remarkable world. The accumulated observations span centuries of Earth time and reveal temporal changes in Saturn's appearance, atmospheric dynamics, and ring structure that reflect both instrumental improvements and genuine evolutionary processes. The future evolution of Saturn's system will unfold according to temporal processes that are already underway, but will require millions or billions of years to reach completion. The gradual migration of moons, the eventual fate of the ring system, the long-term cooling and contraction of the planet, and the ultimate destiny of Saturn's magnetic field all represent temporal processes that connect the present configuration of the system to its far future evolution. As we contemplate Saturn's relationship with time, we begin to appreciate that this distant world serves as both a clock and a calendar for cosmic processes that operate on scales far beyond human experience. The temporal rhythms that govern Saturn's evolution connect this ancient planet to the deepest mysteries of cosmic time and the fundamental processes that shape the universe across billions of years of cosmic history. The temporal landscape surrounding Saturn reminds us that time itself is not the simple, uniform flow that we experience in our daily lives, but a complex, multidimensional phenomenon that varies according to gravitational fields, velocities, and the fundamental structure of space-time itself. In studying Saturn's temporal mysteries, we gain insights into the nature of time that extend far beyond planetary science into the realm of fundamental physics and cosmology. Every measurement we make of Saturn's gravitational field, every observation of its temporal variations, every detection of time-dependent phenomena throughout its system, adds another piece to our understanding of how time operates in gravitational environments throughout the universe. Saturn serves as a natural laboratory where we can study temporal physics under conditions that cannot be replicated in earthly laboratories, providing insights that are relevant to understanding everything from black hole physics to the expansion of the universe itself. The temporal mysteries that surround Saturn continue to unfold as our observational capabilities improve and our theoretical understanding deepens. Each new discovery reveals additional temporal complexity that challenges our assumptions about how time flows through planetary systems and how temporal effects influence the evolution of worlds throughout the cosmos. Saturn's temporal secrets remind us that even the most fundamental aspects of reality, including time itself, become strange and wonderful when viewed through the lens of cosmic scales and gravitational extremes. In the gentle flow of time that carries us through our contemplation of Saturn's mysteries, we find ourselves connected to temporal processes that span from the quantum realm to cosmic evolution, from the brief lifetimes of virtual particles to the billion-year cycles of planetary evolution. Saturn's temporal landscape serves as a bridge between these scales, reminding us that time is not just the backdrop against which cosmic events unfold, but an active participant in the gravitational dance that shapes the structure and evolution of worlds throughout the universe. As we drift deeper into our exploration of Saturn's hidden nature, the temporal mysteries surrounding this ancient world continue to reveal new connections between the flow of time and the fundamental forces that govern cosmic evolution. In understanding Saturn's relationship with time, we gain insights into the temporal architecture of the universe itself and our place within the vast temporal symphony that has been unfolding since the first moments after the Big Bang. The chemical mysteries hidden within Saturn's atmospheric layers reveal secrets about cosmic evolution that stretch back to the very origins of our solar system. Yet the story they tell challenges everything. Your teachers thought they knew about planetary chemistry and the processes that govern atmospheric composition on worlds throughout the universe. What lies concealed within Saturn's swirling clouds is not simply a mixture of hydrogen and helium, but a complex chemical library that preserves death evidence of stellar planetary formation and ongoing chemical processes so exotic they redefine our understanding of what's possible in planetary atmospheres. These are layers atmospheric molecules forged in the extreme conditions created by Saturn's powerful auroras, where high-energy particles from space collide with atmospheric gases to create chemical reactions that operate at temperatures and energies far beyond anything found in terrestrial laboratories. The result is a thin but persistent layer of exotic hydrocarbons, nitriles, and organometallic compounds that paint Saturn's polar regions with subtle hues invisible to human eyes but detectable by sensitive spectroscopic instruments. The trace Saturn's atmosphere, like cosmic spices, tells stories of chemical evolution that span billions of years. Ammonia, hydrogen, methane, sulfide, and phosphine exist in delicate chemical balance, maintained by complex networks of reactions that involve photochemistry in the upper atmosphere, thermochemistry in the deep interior, and transport processes that circulate materials vertically through the entire column. These chemical cycles atmospheric operate according to timescales that range from days to millions of years, creating a temporal hierarchy of chemical processes that makes Saturn's atmosphere one of the most complex chemical systems in our solar system. The phosphine detected particularly in Saturn's atmosphere presents intriguing chemical mystery. This compound should destroy bed rapidly by photochemical reactions in Saturn's upper atmosphere, yet it persists in abundances that suggest continuous replenishment from deep atmospheric sources. The chemical pathways that maintain phosphine concentrations require processes occurring in Saturn's deep interior, where high temperatures and pressures drive reactions that are impossible under normal planetary conditions. The presence of phosphine thus provides a chemical window into processes occurring thousands of kilometers below Saturn's visible cloud surfaces. The isotopic ratios preserved within Saturn's atmospheric constituents carry chemical fingerprints of the stellar environment that existed when our solar system first formed. The ratio of deuterium to hydrogen in Saturn's atmosphere reflects the isotopic composition of the primordial solar nebula, while the ratios of different noble gas isotopes preserve evidence of stellar nuclear synthesis processes that occurred in stars that died before our Sun was born. These chemical signatures make Saturn's atmosphere a repository of information about galactic chemical evolution and the stellar processes that created the elements from which planets form. The vertical distribution of chemical species within Saturn's atmosphere reveals the complex interplay between chemical reactions, atmospheric dynamics, and energy transport processes. Some compounds are concentrated in narrow altitude ranges where specific chemical conditions favor their formation or stability. Others are distributed throughout the atmospheric column by convection processes that transport material from the deep interior to the visible cloud layers. This chemical stratification creates distinct atmospheric zones, each with its own chemical signature and evolutionary history. The seasonal variations in Saturn's atmospheric chemistry demonstrate how chemical processes respond to changing energy inputs and circulation patterns throughout the planet's long year. Some chemical species show dramatic abundance changes as different atmospheric regions experience varying amounts of solar heating, while others remain remarkably stable despite the changing conditions. These seasonal chemical variations provide natural experiments in atmospheric chemistry that reveal how chemical systems adapt to changing boundary conditions over timescales of years to decades. The interaction between Saturn's atmospheric chemistry and its magnetic field creates additional layers of chemical complexity that exist nowhere else in our solar system. Charged particles accelerated by Saturn's magnetosphere drive chemical reactions in the planet's upper atmosphere that produce compounds through pathways involving high-energy particle bombardment, electromagnetic field effects, and plasma chemistry. These magnet processes, or spheric chemical processes, may be responsible for some of the unusual chemical signatures detected in Saturn's polar regions. The organic chemistry occurring in Saturn's atmosphere may be relevant to understanding the prebiotic chemical processes that preceded the origin of life throughout the universe. The complex hydrocarbons, organic compounds create nitriles, and others by photochemical processes in Saturn's upper atmosphere demonstrate how organic chemical complexity can emerge spontaneously in planetary atmospheres under the right conditions, while Saturn's atmospheric conditions are far too extreme to support life as we know it. The organic chemistry occurring there may provide insights into how organic molecules form and evolve in planetary environments. The chemical exchange between Saturn's atmosphere and its ring system creates additional opportunities for exotic chemical processes that involve interactions between gas phase and solid phase materials under the influence of electromagnetic fields and charged particle bombardment. Ring particles bombarded by atmospheric gases may undergo surface chemistry that alters their composition and contributes to the chemical evolution of the ring system. Similarly, material eroded from ring particles may contribute trace constituents to Saturn's atmosphere, creating chemical connections between these seemingly separate components of the Saturn system. The deep atmospheric chemistry occurring in Saturn's metallic hydrogen region represents one of the most exotic chemical environments in our solar system. Under the extreme conditions of temperature, pressure, and electromagnetic field strength that characterize this region, familiar chemical concepts like molecular bonding and electron orbitals break down and give way to quantum mechanical effects that govern the behavior of matter in ways that have no terrestrial analog. The chemical processes occurring in metallic hydrogen may include phenomena like pressure-induced molecular dissociation, quantum tunneling reactions, and electromagnetic field-driven chemical transformations that operate according to principles at the frontier of chemical physics. The role of catalysis in Saturn's atmospheric chemistry adds another layer of complexity to the chemical processes occurring throughout the planet's atmospheric structure. Trace metals and other catalytic species may accelerate chemical reactions that would otherwise proceed too slowly to influence atmospheric composition significantly. These catalytic processes may be particularly important in the middle atmosphere, where moderate temperatures and pressures create conditions favorable for complex chemical reaction networks involving multiple catalytic pathways. The chemical weathering processes that may be occurring on Saturn's moons as a result of bombardment by charged particles from the planet's magnetosphere represent another frontier in understanding the chemical evolution of the Saturn system. The surfaces of moons orbiting within Saturn's radiation belts experience continuous chemical modification through radiolysis, sputtering, and other high-energy chemical processes that gradually alter surface composition and may contribute to the formation of tenuous atmospheres around some of Saturn's smaller moons. The chemical signatures detected in the water vapor plumes erupting from Enceladus provide direct evidence of chemical processes occurring in the moon's subsurface ocean. The detection of molecular hydrogen, organic compounds, and other chemical species in these plumes suggests that complex chemistry is occurring at the interface between Enceladus's ocean and its rocky core. This hydrothermal chemistry may be similar to the processes that occur at deep-sea vents on Earth, environments that support some of the most extreme forms of life on our planet. The hydrocarbon chemistry occurring in Titan's atmosphere and on its surface represents the most complex organic chemistry known to occur naturally in our solar system. The methane cycle that drives weather patterns on Titan involves chemical processes that include photochemical production of complex hydrocarbons, condensation, and evaporation of organic liquids, and surface chemistry involving interactions between liquid hydrocarbons and solid organic compounds. This chemical system operates as a natural laboratory for studying organic chemistry under conditions that may be similar to those that existed on early Earth. The chemical evolution of Saturn's atmosphere over geological time provides insights into how atmospheric composition changes in response to internal evolution, external bombardment, and secular changes in solar luminosity. Computer models of atmospheric chemical evolution suggest that Saturn's atmospheric composition has undergone significant changes since the planet's formation, with some chemical species increasing in abundance, while others have been depleted through escape to space, condensation, or chemical reaction processes. The detection of unusual isotopic signatures in some of Saturn's atmospheric constituents suggests that the planet may have experienced episodes of enhanced bombardment by comets or asteroids that delivered materials with chemical compositions different from the bulk planetary material. These chemical signatures provide evidence for dynamic processes in the early solar system that delivered chemically distinct materials to different planetary environments through impact processes and orbital migration. The chemical processes that may be occurring in Saturn's deep interior, where extreme conditions create environments unlike anything found elsewhere in our solar system, represent the ultimate frontier in understanding planetary chemistry. The formation of exotic phases of matter, the operation of chemical reactions under extreme pressure and temperature conditions, and the chemical evolution of materials over billions of years under these extreme conditions all contribute to creating a chemical environment that may be unique in our solar system. The study of chemical processes throughout the Saturn system has implications that extend far beyond planetary science into the realms of astrobiology, cosmochemistry, and the search for life throughout the universe. The chemical complexity demonstrated in Saturn's atmosphere and throughout its moon system shows how rich and varied chemical evolution can become in planetary environments, providing insights into the chemical processes that may be occurring around other stars and in other planetary systems throughout the galaxy. As we continue to unravel the chemical mysteries surrounding Saturn, each new discovery reveals additional chemical complexity that challenges our understanding of how chemical processes operate in planetary environments. The chemical landscape of the Saturn system serves as a natural laboratory where we can study chemical evolution under conditions that cannot be replicated in terrestrial laboratories, providing insights into the fundamental chemical processes that govern the evolution of matter throughout the universe. The chemical secrets that Saturn continues to reveal remind us that planetary atmospheres are not simple mixtures of gases, but complex chemical systems where multiple processes interact to create chemical environments of extraordinary richness and complexity. In studying Saturn's chemical mysteries, we gain insights into the chemical processes that shape planetary evolution throughout the cosmos and the chemical foundations that may support the emergence of life in environments far more diverse and exotic than anything found on Earth. Every spectroscopic observation of Saturn's atmosphere, every measurement of chemical abundances throughout its system, every detection of new chemical processes adds another piece to our understanding of how chemistry operates in planetary environments throughout the universe. Saturn's chemical mysteries continue to unfold as our analytical chemical processes under capabilities improve and our theoretical understanding of extreme conditions becomes more sophisticated, promising new discoveries that will further expand our understanding of cosmic chemical evolution and the chemical processes that connect planets, stars, and life throughout the universe. The chemical revelations within Saturn's domain extend into territories that touch the very essence of existence itself, where matter transforms according to principles that seem more like alchemy than conventional chemistry. What emerges from the deepest layers of this exploration is not just knowledge about a distant planet, but profound insights into how the universe creates, destroys, and recreates the fundamental building blocks of reality across scales that span from atomic interactions to galactic evolution. Deep within Saturn's atmospheric cathedral, where no sunlight has ever penetrated and no earthly instrument will ever venture, chemical processes unfold that represent the universe's most exotic experiments in molecular architecture. Here, in regions where pressure exceeds 1,000,000 times Earth's atmospheric pressure and temperatures rival the surface of red dwarf stars, familiar elements abandon their terrestrial behaviors and embrace quantum mechanical states that transform the very meaning of chemical bonding. In these hidden depths, carbon atoms stripped from methane molecules don the diamond's simply formed rain that scientists have theorized. Instead, they participate in chemical reactions so extreme phases that they create of matter that exists nowhere else in our solar system. Under pressures that compress atomic structures beyond recognition, carbon may form crystalline networks that conduct electricity like metals while maintaining the hardness of diamond, creating materials that would revolutionize technology if we could somehow recreate them under earthly conditions. The hydrogen that dominates Saturn's composition undergoes its own remarkable transformation in these crushing depths. As individual hydrogen atoms lose their electrons and merge into the metallic hydrogen ocean that generates Saturn's magnetic field, they create chemical environments where the distinction between atomic and molecular chemistry breaks down entirely. In this realm, chemical reactions may proceed through quantum tunneling effects, where atoms pass through energy barriers that should be insurmountable, creating reaction pathways that have no analog in terrestrial chemistry. The helium that slowly separates from hydrogen throughout Saturn's interior doesn't simply sink toward the core through gravitational settling. As it descends through regions of increasing pressure and temperature, helium atoms encounter chemical environments where they may form temporary compounds with other elements before continuing their journey towards Saturn's center. This helium migration creates chemical gradients that influence everything from the planet's magnetic field generation to the subtle atmospheric dynamics visible at Saturn's cloud tops. The trace elements dissolved throughout Saturn's atmospheric ocean tell evolution that connects stories of chemical this distant world to the stellar furnaces where heavy elements were first forged billions of years ago. Iron, nickel, silicon, and other metals exist in Saturn's interior in concentrations that seem insignificant compared to the overwhelming abundance of hydrogen and helium. Yet these trace constituents play crucial roles in catalyzing chemical reactions and influencing physical processes throughout the planet's structure. As these metallic elements circulate through Saturn's convecting interior, they participate in chemical processes that may include the formation of metallic alloys with properties unlike anything found on rocky planets. Under the extreme conditions within Saturn's metallic hydrogen ocean, iron and nickel may form compounds with hydrogen itself, creating materials that blur the line between conventional metals and exotic phases of matter that exist only under extreme pressure and temperature conditions. The ongoing chemical evolution of Saturn's interior creates feedback loops that connect chemical processes to magnetic field generation, atmospheric dynamics, and even the behavior of the planet's ring system. As chemical species migrate vertically through Saturn's interior, they alter the electrical conductivity of different atmospheric layers, which in turn influences the convection patterns that drive the planet's magnetic dynamo. These magnetic field variations then affect the electromagnetic environment throughout the Saturn system, creating cascading effects that connect chemistry occurring thousands of kilometers below Saturn's surface to phenomena observable in the planet's rings and auroral displays. The chemical fingerprints preserved in Saturn's atmospheric composition provide a direct link to the chemical environment that existed in our solar system's formation region over 4.5 billion years ago. The noble gas abundances, isotopic ratios, and trace element concentrations locked within Saturn's atmosphere represent a fossil record of the chemical conditions that prevailed when planets were first accreting from the solar nebula. This chemical archive makes Saturn not just a planet, but a repository of information about galactic chemical evolution and the stellar processes that created the elements from which all planetary systems form. The seasonal chemical variations that occur throughout Saturn's extended year demonstrate how chemical systems respond to changing energy inputs over timescales that dwarf human experience. As different regions of Saturn's atmosphere experience decades-long summers and winters, chemical reaction rates, photochemical processes, and transport phenomena all adjust to the changing conditions. These seasonal adaptations create natural experiments in atmospheric chemistry that reveal how chemical systems maintain stability while adapting to changing boundary conditions. The chemical connections between Saturn and its diverse family of moons create opportunities for material exchange and chemical evolution that operate across the entire Saturn system. Atmospheric gases escaping from Saturn may contribute to the tenuous atmospheres surrounding some moons, while material eroded from moon surfaces by charged particle bombardment may eventually find its way into Saturn's atmosphere. This chemical interchange creates evolutionary pathways that connect the chemical evolution of Saturn itself to the geological and atmospheric processes occurring throughout its satellite system. The discovery of complex organic molecules in the plumes erupting from Enceladus has revealed that the Saturn system harbors chemical processes that may be directly relevant to understanding the origins of life throughout the universe. The chemical diversity detected in these water vapor eruptions includes not only simple organic compounds, but complex molecules that represent some of the chemical building blocks necessary for biological processes. While the extreme conditions within Enceladus's subsurface ocean make it unlikely to support life as we understand it, the chemical processes occurring there demonstrate how chemical complexity can emerge in environments far removed from traditional concepts of habitability. The hydrocarbon chemistry dominating Titan's surface and atmosphere represents the most complex organic chemical system known to exist naturally beyond Earth. The methane lakes and rivers that cover portions of Titan's surface participate in chemical cycles that involve evaporation, precipitation, surface chemistry, and atmospheric photochemistry operating in an integrated system that has been evolving for billions of years. This chemical system operates as a natural laboratory for studying how organic chemistry evolves in planetary environments, providing insights into the chemical processes that may have operated on early Earth and continue to operate on worlds throughout the galaxy. The chemical processes occurring within Saturn's rings represent another frontier in understanding how chemistry operates in the unique environment of planetary ring systems. Ring particles composed primarily of water ice undergo continuous chemical modification through bombardment by charged particles, exposure to ultraviolet radiation, and interactions with trace gases from Saturn's atmosphere. These chemical weathering processes gradually alter the composition and optical properties of ring material, contributing to the complex color variations and structural features observed throughout Saturn's magnificent ring system. And so, we reach the end of our cosmic journey together, having traveled through realms that your textbooks could never have imagined. From singing rings that create celestial symphonies to diamond rain falling through metallic hydrogen oceans, from moons harboring hidden seas that could cradle life to electromagnetic storms that dwarf our entire planet, Saturn has revealed itself as far more than a distant world with pretty rings. It stands as a testament to the universe's infinite capacity for wonder, a reminder that even in our own cosmic neighborhood, mysteries await that challenge everything we thought we knew about the nature of reality itself. As you drift off to sleep tonight, remember that you are connected to these cosmic processes through the very atoms in your body, forged in stellar furnaces and shaped by the same forces that govern Saturn's magnificent dance through space and time. Sweet dreams, fellow cosmic wanderer.